Right now, 15 billion miles from Earth, humanity's most distant messenger is revealing secrets that are, honestly, rewriting our understanding of space. Voyager 1 crossed into interstellar space back in 2012, becoming the first human-made object to leave our solar system's protective bubble. But after a terrifying communication blackout in 2023, the spacecraft came back online with data that absolutely stunned scientists. The space between stars isn't the empty void we imagined. It's actually a dynamic, structured environment filled with cosmic weather, invisible boundaries, and phenomena that challenge everything we thought we knew about our galaxy.
The Silent Crisis.
April 2024 brought relief after months of cosmic terror. Voyager 1 had gone completely silent, transmitting only garbled signals that made no sense to NASA engineers at the Jet Propulsion Laboratory. After 46 years of faithful service, humanity's most distant explorer was dying. The culprit was a corrupted memory chip, likely damaged by a cosmic ray strike. The very phenomenon Voyager was studying had wounded it. Engineers faced an unprecedented challenge, performing brain surgery on a spacecraft using 1970s technology from 15 billion miles away, where radio signals take over 22 hours for a round trip. The rescue operation required rerouting code into backup memory areas, essentially giving CPR to a robot that predated most modern computers. By May 2024, the patient showed signs of life, with all 4 science instruments gradually coming back online. This wasn't just an engineering triumph, it was humanity's lifeline to the only measurements we have from beyond our solar system.
Magnetic mysteries beyond the edge.
The first shock came from Voyager's magnetometer readings after crossing the heliopause. Scientists expected some differences, but the interstellar magnetic field showed a dramatic misalignment compared to our sun's magnetic influence. This wasn't a gradual transition, it was a sharp boundary suggesting something far more significant than anyone had anticipated. The readings point to Voyager 1 entering a magnetic turbulence zone where galactic magnetic fields twist and reconnect in ways that could, honestly, reshape our understanding of galactic structure. These aren't small ripples in space, they're fundamental forces operating on scales larger than our entire solar system. The magnetic field orientations Voyager measures might even channel cosmic material into denser regions, potentially influencing where new stars form in our region of the galaxy. Each measurement reveals that interstellar space has its own magnetic weather patterns, invisible highways of force that guide particles across vast cosmic distances. The spacecraft continues to detect these magnetic anomalies, proving that the space between stars is far more structured and dynamic than anyone predicted.
The Cosmic Ray Avalanche.
Crossing into interstellar space triggered an immediate and honestly shocking discovery. Voyager's cosmic ray detector recorded a sharp spike in high-energy particles accelerated to nearly light speed by distant supernovae and black holes. The increase wasn't gradual, it was abrupt, like stepping through an invisible barrier. This revelation exposed how effectively our sun's heliosphere shields Earth from the harsh radiation environment of interstellar space. We're living in a cosmic oasis, protected from particle bombardment that would be lethal to unshielded life. But the pattern isn't uniform. Voyager has detected systematic variations, suggesting natural radiation corridors, cosmic highways where particles preferentially flow. These measurements hint at larger galactic structures, possibly ancient scars left by stellar explosions that shaped our neighborhood millions of years ago. The spacecraft may be detecting pressure gradients that map onto invisible architecture spanning light years. Each cosmic ray measurement reveals more about the galactic environment, showing that we're not just measuring local conditions, but glimpsing the aftermath of cataclysmic events that continue to influence our cosmic neighborhood today.
Whispers in the Void.
You know, the silence of space doesn't actually exist. Voyager's plasma wave instrument has completely shattered the old myth of cosmic emptiness by detecting these constant low-frequency oscillations that just permeate interstellar space. And these aren't just random fluctuations, no, they're structured signals, suggesting that the space between stars has its own unique acoustic signature. The instrument has even picked up multiple plasma density spikes, kind of like pressure waves moving through an invisible medium out there. Scientists think these could be shock fronts left behind by ancient supernovae that exploded thousands of years ago, still rippling through the interstellar medium today. So Voyager isn't just drifting through emptiness, it's flying through an invisible fog with its own distinct layers and properties. Some regions are hotter, others are denser, and together they create this complex three-dimensional structure that actually resembles weather patterns a lot more than the uniform void scientists once expected. This cosmic hum, it's really the background activity of our galaxy, a constant whisper from the space between stars. The plasma waves are revealing that interstellar space has its own dynamics, its own currents and temperatures, creating an environment that's far more active than anyone could have imagined.
Interstellar weather patterns.
Voyager 1 has actually passed through at least 2 distinct interstellar cloudlets since crossing the boundary, and this has revealed that the space between stars has structure, kind of like an ocean with currents and eddies. These aren't visible clouds though, they're regions where the plasma, dust, and gas density suddenly changes by factors of 2 or even 3 times. The spacecraft's instruments show evidence of these structured plasma ripples with clear boundaries, almost like atmospheric fronts out in space. NASA scientists now believe our sun is moving through the local interstellar cloud, and Voyager is helping to define its outer edges right now. This cloud exists inside the much larger local bubble, which is this enormous cavity created by ancient supernovae. These density shifts, they actually affect Earth's cosmic ray exposure over millennia. As our solar system drifts through different interstellar environments at 450,000 miles per hour, the radiation environment at Earth subtly changes, and that can potentially affect cloud formation and even mutation rates in living organisms. Voyager is showing us that interstellar space isn't just a straight path, it's really a gauntlet of invisible forces that create this complex, ever-changing cosmic landscape, complete with its own weather systems and boundaries.
Digital resurrection.
So, the 2023 communication crisis nearly ended humanity's only direct window into interstellar space. For months, Voyager 1 was transmitting incomprehensible data, its memory corrupted by cosmic ray bombardment. NASA engineers were suddenly facing one of their greatest challenges: remotely repairing a spacecraft that's actually older than most of their careers, and doing it with technology from the Carter administration no less. The solution took unprecedented ingenuity, rerouting decades-old code into backup memory areas while somehow maintaining all the critical functions across a 15 billion-mile gap. And every command took 22 hours to reach the spacecraft, so real-time troubleshooting was just impossible. The team basically performed remote surgery on a patient they couldn't see or touch. In April 2024, they finally had a breakthrough when basic telemetry resumed, and that was followed by the gradual revival of the scientific instruments. By June 2024, all 4 active science instruments were functioning again. This wasn't just an engineering triumph, it was humanity's lifeline to the only measurements we have from beyond our solar system's protective bubble. The rescue operation showed that even 1970s technology could be revived through innovative engineering, buying us precious additional years of interstellar data collection.
Mapping the invisible galaxy.
Voyager 1 is creating something, well, truly unprecedented, a navigational chart of interstellar space. With every data packet sent back, scientists are able to construct 3-dimensional models of the Milky Way's magnetic and radiation zones, using Voyager's measurements as crucial anchor points. This, honestly, represents the first real-scale cartography of our stellar neighborhood. It's a bit like having a weather satellite, but for the cosmos. The cosmic ray gradients, particle density readings, and magnetic field orientations are revealing natural shields and danger zones, and these could really determine whether humans can safely venture beyond our solar system. The radiation environment that Voyager measures is far more intense than what astronauts face in Earth orbit, which makes these maps absolutely crucial for any future interstellar missions. Some astrophysicists even believe the structures Voyager is mapping may influence star formation patterns across our galactic region. Quietly, the spacecraft is drawing the first blueprint of the space between stars, creating detailed models that get refined with every new measurement. This mapping project has, well, become the foundation for understanding how to navigate the void between stars, potentially guiding future spacecraft through the safest corridors of interstellar space.
The protected oasis.
Voyager's measurements have revealed a profound truth about Earth's place in the cosmos. Our solar system exists within a protective bubble that shields us from an environment far more hostile than anyone realized. The dramatic increase in cosmic radiation beyond the heliopause demonstrates how effectively the sun's magnetic field deflects dangerous particles that would otherwise bombard our planet. This discovery reframes Earth not just as our home, but as our shelter in a cosmic storm. The interstellar medium contains radiation levels that would pose serious threats to unprotected life, making our heliosphere a crucial barrier against galactic hazards. Voyager's data shows that this protection varies as our solar system moves through different interstellar environments over millions of years. The spacecraft's measurements of density variations and magnetic field changes suggest our cosmic neighborhood is far from uniform. We're traveling through a complex landscape of radiation zones, magnetic boundaries, and plasma clouds that create an ever-changing environment around our solar system. Understanding these variations helps explain long-term climate patterns and cosmic ray exposure cycles that may have influenced life's evolution on Earth.
The eternal journey.
Beyond its scientific mission, Voyager 1 carries humanity's most enduring message to the cosmos. The golden record attached to the spacecraft contains sounds, music, greetings in 55 languages, and 116 images representing Earth's diversity. This time capsule is engineered for extreme longevity, designed to survive over 1 billion years in the harsh environment of space. In approximately 40,000 years, Voyager 1 will make its closest approach to the star Gliese 445, passing within 1.6 light-years of this distant red dwarf. Long after Earth's continents have shifted beyond recognition, long after human civilization has evolved or disappeared, this record will endure. Voyager represents humanity's most lasting trace in the universe, an ambassador that will outlive our species. No other human object will leave the heliosphere for decades, making Voyager literally our longest-lasting monument. The spacecraft transforms from a scientific probe into something more profound, a message frozen in time, carrying the essence of who we were in 1977 across the galaxy for eons to come. This cosmic time capsule gives Voyager significance that transcends its scientific achievements, becoming humanity's first tentative step into eternity.
Redefining reality.
The space beyond our solar system isn't the featureless void astronomers once imagined. Voyager 1 has revealed a dynamic structured environment with weather patterns, magnetic topography, and radiation zones that shape our galaxy's invisible architecture. The transition from our solar bubble to interstellar space isn't clean. It's messy, complex, and honestly pretty fascinating. Magnetic fields don't align as expected, radiation environments change dramatically, and plasma waves suggest constant activity we never knew existed. Voyager's discoveries prove that interstellar space has layers, fronts, and boundaries, creating a textured cosmic landscape far more intricate than anyone predicted. The spacecraft continues operating on borrowed time, with NASA making difficult decisions about which instruments to shut down as power gradually fades. Early 2025 saw the cosmic ray detector powered down to extend the overall mission, but 3 science instruments continue transmitting their faint 23-watt signals across the cosmic void. Each day, Voyager 1 operates as a gift of knowledge from humanity's only direct sampling of the space between stars, rewriting textbooks with every transmission from the interstellar frontier. Voyager 1 reached the other side, and the reality is more extraordinary than fiction. The interstellar medium isn't empty. It's a structured, dynamic environment that challenges our understanding of cosmic architecture. From magnetic mysteries to plasma whispers, from radiation avalanches to cosmic weather patterns, Voyager continues revealing secrets that rewrite astronomy textbooks. This incredible journey proves that sometimes the most profound discoveries come from the simplest act of reaching beyond our boundaries. If you love real space exploration without the hype, smash that like button and subscribe to Stellar Tech for more mind-blowing cosmic discoveries. The universe is far stranger than we thought. September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The Kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lyndon Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet, orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target. Since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos's center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos's orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Chang'e, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution pattern suggested the moonlit surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos' structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos' rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos's location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their space situational awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest, with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols, which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats, but it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future. Voyager 1, a tiny spacecraft the size of a car, is drifting through the unimaginable darkness of space, 14.5 billion miles from Earth. But nearly 50 years later, Voyager is still alive, defying the odds. Recently, This legendary probe has encountered something in the void that has scientists both amazed and deeply concerned. What has there found Voyager? The data streaming back suggests phenomena that challenge everything we thought we knew about interstellar space. Today, we explore Voyager's impossible encounter and what it means for humanity's future among the stars. The birth of a star sailor. The story of Voyager 1 began in the era of Cold War ambition, when NASA sought to expand humanity's horizons beyond Earth orbit. Under the leadership of Dr. Edward Stone, Voyager 1 was designed as a robust spacecraft capable of a grand tour of the outer planets, the first of its kind. Launched on September 5, 1977, from Cape Canaveral, it journeyed towards Jupiter with an array of scientific instruments, including the cosmic ray detector and plasma wave instrument. The spacecraft was engineered to survive decades of space exposure, carrying the hopes of mankind as it ventured boldly where no one had gone before. Dr. Stone's decade-long stewardship ensured the mission's remarkable longevity, setting the stage for an unprecedented exploration of our solar system. Built with 1970s technology that would seem primitive by today's standards, Voyager 1 was nevertheless equipped with instruments sensitive enough to detect the faintest signals from the cosmos. The spacecraft's nuclear power source, designed to last far beyond its primary mission, would prove crucial for its extended journey into the unknown. This remarkable engineering feat would soon carry humanity's message to the stars and beyond. The Grand Tour. Voyager 1's Grand Tour of the solar system became legendary, lasting over 12 years and bringing humanity close to the gas giants Jupiter, Saturn, Uranus, and Neptune. During flybys, it sent back unparalleled images and life-changing data that redefined our understanding of these colossal planets. Notably, the encounter with Jupiter revealed the planet's turbulent atmosphere and intense magnetic field, reshaping planetary science forever. The spacecraft discovered active volcanoes on Jupiter's moon Io and revealed the complex structure of Saturn's rings in unprecedented detail. Subsequent visits to the outer planets expanded our knowledge of ice giants and their mysterious moon systems. Each planetary encounter used gravitational assist to propel Voyager faster toward the edge of the solar system, a trajectory carefully calculated to maximize scientific return. The spacecraft's cameras captured images that became iconic symbols of human exploration, including the famous pale blue dot photograph of Earth taken from 4 billion miles away. Voyager's trajectory, programmed for a final sprint beyond the solar system, demonstrated NASA's engineering brilliance in interplanetary travel. Today, its legacy continues as it ventures into interstellar space, humanity's first emissary beyond the protective bubble of our sun's influence. The Golden Record. The Golden Record aboard Voyager 1 is a time capsule destined to outlast humanity itself, containing sounds and images representing Earth's diversity. Curated by Dr. Carl Sagan and a committee of scientists and artists, the record includes greetings in 55 languages and music spanning cultures and epochs. Encased in an engraved gold-plated copper disc, it serves as a cosmic message in a bottle, intended for any intelligent life that may encounter it in the distant future. The record also contains scientific information about Earth's location, using pulsar maps devised by Dr. Frank Drake, providing a cosmic roadmap for potential discoverers. Despite its age, the Golden Record remains a testament to human curiosity and hope across the void of space, symbolizing peace and universality. The record includes sounds of Earth, from ocean waves to human heartbeats, from classical music to the laughter of children. It represents humanity at its best, showcasing our diversity while emphasizing our common bonds. Voyager's legacy is as much cultural as scientific, immortalizing humanity beyond our solar system boundaries. This golden message continues its journey through the cosmos, carrying our hopes and dreams to destinations unknown. Years in the void. Years of drifting through the cold void beyond our solar system, Voyager 1 has defied all expectations for spacecraft longevity. Since crossing the heliopause in 2012, it has continuously sent back data about interstellar space despite operating far beyond its design limits. Engineers at NASA Jet Propulsion Laboratory, led by Dr. Suzanne Dodd, have managed to keep the spacecraft operational despite dwindling power supplies and aging components. Voyager's instruments continue to measure the harsh radiation environment far beyond any planet's protective magnetosphere, revealing a cosmos more dangerous and dynamic than anyone imagined. The spacecraft's telemetry reveals vital signs including temperature readings and electrical system status. a testament to the incredible engineering resilience of 1970s technology still performing flawlessly in the most hostile environment known. Each year, Voyager's plutonium power source weakens, forcing mission controllers to make difficult decisions about which instruments to shut down to conserve energy. Yet the spacecraft persists, transmitting scientific data across billions of miles of empty space. Voyager 1's longevity contrasts sharply with initial mission expectations, with scientists noting it has become humanity's longest-lived emissary in the cosmos, far exceeding all predicted operational timelines. Crossing the boundary. Voyager 1's historic crossing of the heliopause marked humanity's first journey into true interstellar space, a milestone that redefined our understanding of the cosmic frontier. The spacecraft's instruments, including sophisticated sensors and detection equipment, began recording phenomena unlike anything seen within our solar system's protective bubble. Lead scientist Dr. George Glockler from the University of Minnesota explains the significance of these observations, revealing magnetic field turbulence and unexpected plasma oscillations that challenge existing models of the interstellar medium. The boundary between solar and galactic space proved far more complex and dynamic than theoretical predictions suggested, showing multiple layers and transitional zones rather than a clean separation. Voyager's data revealed that interstellar space is not the quiet, empty void scientists once imagined, but rather a region filled with electromagnetic activity and cosmic phenomena. The spacecraft detected charged particles moving at incredible velocities, evidence of ancient stellar explosions and cosmic events that occurred millions of years ago. These measurements provided the first direct sampling of materials from beyond our solar system, offering insights into the composition and behavior of the galaxy itself. Voyager's continuing transmission from this unexplored realm offers unprecedented insights into the boundary between solar influence and the vast galactic ocean beyond our protective heliosphere. Signals from nowhere. In late 2023, Voyager 1 went mysteriously silent, sparking fears among mission scientists who had dedicated decades to the project. Analysis revealed a corrupted memory chip, likely damaged by a high-energy cosmic ray that struck the spacecraft with devastating precision. Immediate action by the Jet Propulsion Laboratory team, including Flight Director Dr. Melissa Brown, involved rerouting computer operations to back up memory areas while working across an impossible distance. This delicate software workaround, performed from Earth with signals taking over 22 hours each way, required extraordinary precision and patience from the engineering team. The rescue operation demonstrated incredible human ingenuity, essentially performing remote brain surgery on a patient billions of miles away using technology older than most of the engineers working on it. When Voyager finally responded, it brought relief to scientists worldwide who had feared losing humanity's most distant explorer forever. The incident highlighted both the spacecraft's vulnerability and resilience, showing how a single cosmic particle could threaten decades of scientific discovery. The successful restoration of communication proved that even in the depths of interstellar space, human determination and technical expertise could overcome seemingly impossible odds and continue our journey of cosmic exploration. The temperature mystery. Voyager's instruments have detected bizarre temperature anomalies in the interstellar medium that defy current scientific understanding of cosmic thermodynamics. The spacecraft's sensors recorded unexpected heat signatures and thermal variations that suggest unknown energy sources operating in supposedly empty space. Dr. Reka Winslow from the University of Michigan analyzed data showing these temperature fluctuations correlate with mysterious electromagnetic activity that creates complex thermal gradients across vast distances. These findings indicate dynamic processes previously unknown to science, with energy transfers occurring through mechanisms that current physics cannot fully explain. The spacecraft's thermal sensors detected variations that challenge existing models of interstellar space, revealing an environment far more active and energetically complex than anticipated. These thermal anomalies persist across the spacecraft's trajectory, creating a puzzle that has scientists scrambling to develop new theories about energy distribution in interstellar space. The temperature readings suggest that the void between stars may harbor energy sources or phenomena that could revolutionize our understanding of cosmic physics. Some researchers speculate these thermal signatures could indicate the presence of dark matter interactions or unknown electromagnetic processes that operate on galactic scales, opening entirely new avenues for astrophysical research and discovery. Changing course. Maintaining control over a spacecraft traveling through the depths of interstellar space requires unprecedented precision in navigation techniques and trajectory management. Dr. Carlos Hernandez from NASA Goddard Space Flight Center leads efforts to execute delicate course corrections on Voyager 1, despite the enormous challenges posed by distance and communication delays. These trajectory adjustments must account for the spacecraft's changing orientation, limited fuel reserves, and the gradual degradation of its attitude control systems after decades of operation. The complex calculations required for each maneuver consider gravitational influences from distant stars, the pressure of interstellar particles, and the spacecraft's slowly declining power output. These adjustments demonstrate unparalleled precision in space navigation, requiring engineers to predict and compensate for factors that won't be observable for hours due to signal travel time. Each course correction represents a carefully calculated gamble, as there are no second chances when working with such precious and irreplaceable scientific assets. The navigation team must balance scientific objectives with spacecraft preservation, making difficult decisions about energy expenditure and pointing accuracy. Despite these challenges, Voyager continues to maintain its scientific mission while heading toward an eventual encounter with the star AC plus 79 3888 in approximately 40,000 years. Ghost in the machine. Recent months have seen Voyager 1's onboard computer systems exhibit mysterious glitches that have puzzled mission engineers and raised concerns about artificial intelligence anomalies. Led by Dr. Ananya Singh at NASA's Jet Propulsion Laboratory, the team closely monitors these strange behaviors manifesting as unexplained error codes and signal irregularities that don't match any known failure modes. The anomalies appear almost intelligent in nature, as if something within the spacecraft's systems is learning and adapting to its environment in ways the original programmers never intended. Some engineers speculate these phenomena arise from cosmic radiation effects interacting with the spacecraft's aging electronics in unexpected ways, while others wonder if decades of exposure to interstellar conditions have somehow altered the computer's fundamental operations. The spacecraft occasionally transmits data patterns that seem to contain information beyond its programmed capabilities, leading to speculation about whether the harsh environment of space might be inducing evolutionary changes in electronic systems. Diligent troubleshooting and software updates aim to preserve communication integrity, but the mysterious behaviors continue to manifest despite all efforts to understand or control them. These electronic anomalies represent one of the most puzzling aspects of Voyager's extended mission. Patterns within patterns. Recent analysis of Voyager's long-term data has revealed subtle but persistent patterns in cosmic ray measurements and magnetic field variations that suggest influences from unknown astrophysical sources. Dr. Emilia Garza, a heliophysics expert from the University of Texas, notes the discovery of quasi-periodic oscillations that appear to originate from deep space phenomena beyond our current understanding. These patterns within patterns challenge assumptions about the uniformity of interstellar space, instead revealing a complex structure operating on multiple scales and timescales that scientists are only beginning to comprehend. The oscillations show characteristics that don't match any known natural phenomena, leading some researchers to speculate about possible artificial origins or previously unknown physical processes occurring in the galactic environment. Voyager's instruments detect synchronizations and correlations in the data that seem too organized to be purely random, suggesting underlying mechanisms that organize matter and energy across vast cosmic distances. These discoveries have profound implications for our understanding of how the galaxy operates, potentially revealing hidden structures or forces that influence the behavior of matter and energy throughout interstellar space. The patterns continue to evolve as Voyager travels deeper into unexplored regions, providing humanity with its first glimpse into the true architecture of our galactic neighborhood and the mysterious forces that shape it. Voyager 1 continues its impossible journey into the cosmic unknown, revealing mysteries that challenge our understanding of the universe itself. From strange temperature anomalies to unexplained computer behaviors, this tiny spacecraft has encountered phenomena that suggest the cosmos holds secrets far beyond our current knowledge. As it drifts ever deeper into interstellar space, Voyager carries not just our scientific instruments, but our hopes and fears about what lies beyond our protective solar bubble. Subscribe to Stellar Tech for more revelations about humanity's greatest adventure and the discoveries that await us in the darkness between the stars.
Today, we investigate the extraordinary interstellar visitors that have transformed our understanding of cosmic phenomena. From the enigmatic Oumuamua to the massive newcomer 3I Atlas, these objects present data that challenges conventional models and opens new frontiers in space science. Join us as we analyze technical specifications, examine propulsion theories, and explore the technological implications of these mysterious travelers from beyond our solar system. Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS telescope array in Hawaii detected an unprecedented object exhibiting characteristics unlike any previously catalogued celestial body. Oumuamua, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, displayed non-gravitational acceleration patterns inconsistent with standard orbital mechanics. Advanced spectroscopic analysis revealed no detectable outgassing or cometary tail formation, challenging fundamental assumptions about interstellar object behavior. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that this visitor might represent an artificial light sail utilizing solar radiation pressure for propulsion. Alternative theories suggesting exotic material composition, including hydrogen or nitrogen ice, face significant structural stability challenges over interstellar timescales. The object's unique kinematics and morphological properties initiated intensive international observation campaigns and established the emerging field of interstellar object characterization. Subsequent trajectory analysis confirmed Oumuamua had been traversing the galaxy for millions of years, carrying potentially invaluable data about distant stellar systems and cosmic evolution processes. UFO-UAP encounters and theories. Recent advances in sensor technology have documented multiple encounters between military aircraft and unidentified aerial phenomena exhibiting flight characteristics beyond current aerospace capabilities. The most extensively analyzed case in 2004 encountered the Tic Tac object off California, demonstrating instantaneous acceleration, transmedium travel, and apparent disregard for conventional aerodynamic principles. Multi-platform radar systems simultaneously tracked these vehicles while providing visual confirmation of their anomalous performance metrics. Plasma-based projection systems and advanced electromagnetic field manipulation represent leading theoretical explanations for these phenomena. Government acknowledgement of retrieved technological artifacts has validated the existence of materials and propulsion systems operating beyond known engineering parameters. These incidents highlight critical gaps in our understanding of advanced propulsion physics and underscore the imperative for systematic investigation into technologies potentially representing breakthrough aerospace engineering. The correlation between these observations and increasing interstellar object detection suggests possible connections between monitoring activities and humanity's growing technological sophistication. Bob Lazar analysis. Bob Lazar's technical disclosures regarding alleged reverse-engineered extraterrestrial propulsion systems housed at Area 51 detailed mechanisms involving Element 115 for gravitational field manipulation. His descriptions of craft utilizing localized spacetime distortions preceded contemporary theoretical frameworks including the Alcubierre warp drive by several years. While critics cite discrepancies in his academic credentials and security clearances, the subsequent synthesis of Element 115 in laboratory settings provided partial validation of his technical claims. Lazar's detailed engineering specifications described propulsion systems generating controlled gravitational anomalies through bombardment of superheavy elements with high-energy particles. Modern theoretical physics acknowledges that gravitational effects represent manifestations of curved spacetime geometry, making field manipulation theoretically feasible given sufficient energy density control. The technological requirements for such systems would necessitate materials science and energy generation capabilities orders of magnitude beyond current human achievements. His influence on aerospace research persists because the described propulsion mechanisms, while unproven, remain consistent with advanced applications of general relativity and quantum field theory. Light sail hypothesis. Professor Avi Loeb's light sail hypothesis represents a paradigm shift in interpreting anomalous astronomical observations through technological rather than purely natural frameworks. Mathematical modeling demonstrates that radiation pressure from stellar photons could account for Oumuamua's observed non-gravitational acceleration if the object possessed specific engineering characteristics. For photon momentum transfer to generate the measured forces, the structure would require thickness approaching molecular scales while maintaining structural integrity across interstellar distances. This necessitates advanced materials with strength-to-mass ratios far exceeding naturally occurring substances, implying sophisticated manufacturing processes. Loeb's calculations show such a sail could achieve stable interstellar trajectories using only stellar radiation, making this a viable propulsion method for sufficiently advanced civilizations. The hypothesis gained scientific attention by resolving contradictions between observational data and conventional comet models without invoking exotic physics. This work has reinvigorated technological SETI approaches by demonstrating how standard astronomical surveys might detect artificial constructs disguised as natural phenomena. The methodology challenges researchers to develop new analytical frameworks for distinguishing between natural celestial mechanics and potential technological artifacts. 3I Atlas, the new discovery. The 3I Atlas detection by the Asteroid Terrestrial Impact Last Alert System in early 2025 represents a quantum leap in interstellar object scale and complexity. Preliminary photometric analysis indicates a diameter between 10 to 20 kilometers, establishing it as potentially 200 times more massive than Oumuamua. Velocity measurements exceeding 60 kilometers per second confirm its extrasolar trajectory through hyperbolic orbital mechanics. Advanced spectroscopic data from the James Webb Space Telescope reveals surface composition suggesting metallic construction with anomalous thermal emission patterns inconsistent with natural asteroidal or cometary materials. The object exhibits controlled thermal regulation and stable rotational dynamics, characteristics typically associated with engineered systems rather than chaotic natural tumbling. Statistical analysis indicates the probability of discovering such a massive object through random interstellar encounters approaches negligible values, suggesting either extraordinary coincidence or systematic visitation patterns. Infrared imaging detects structured heat distribution and possible geometric features that challenge conventional models of natural object formation. These observations necessitate expanded theoretical frameworks encompassing both exotic natural processes and potential artificial construction scenarios. Atlas Telescope System. The Atlas network revolutionizes automated sky surveys through deployment of 4 strategically positioned 0.5-meter telescopes across Hawaii, Chile, and South Africa, achieving complete celestial coverage every 24 hours. Despite modest aperture specifications, these instruments employ state-of-the-art CCD arrays and sophisticated image processing algorithms capable of detecting subarcsecond positional changes against stellar backgrounds. Real-time data processing utilizes machine learning protocols trained on millions of astronomical images to identify anomalous motion signatures indicative of fast-moving objects. The University of Hawaii manages this network with NASA funding, establishing new paradigms for distributed observation systems. Atlas technology demonstrated exceptional capability in early detection of 3I Atlas, providing crucial lead time for coordinated international observation campaigns before the object's closest approach. Automated detection algorithms process terabytes of nightly data, flagging suspicious objects within hours of observation for immediate follow-up by major observatories worldwide. This high-cadence survey methodology has transformed asteroid detection from periodic manual searches to continuous automated monitoring, dramatically increasing discovery rates of rare cosmic phenomena and potentially hazardous objects. Scientific theories and debates. The astrophysical community remains divided over 3I Atlas classification, with competing hypotheses attempting to reconcile observational anomalies with established physics. The hydrogen iceberg model proposes exotic solid-state hydrogen formation in deep interstellar space, though structural mechanics calculations indicate rapid sublimation rates incompatible with observed stability. Nitrogen fragment theory suggests compositions analogous to Pluto's surface materials, potentially explaining thermal signatures without conventional outgassing patterns. Dr. Alan Fitzsimmons advocates natural origin interpretations while emphasizing the critical need for comprehensive spectroscopic datasets before considering exotic explanations. Fundamental inconsistencies persist between measured acceleration vectors and detectable volatile emission rates, challenging basic cometary physics models. Statistical mechanics analysis reveals discovery probabilities for objects of this scale through random encounters effectively approach zero, forcing reconsideration of either size distribution models or visitation patterns. Advanced computer simulations struggle to reproduce observed characteristics using purely natural formation processes, suggesting either unknown physics or engineered construction. Future detection technology. The Vera C. Rubin Observatory in Chile represents next-generation astronomical detection capabilities, featuring an unprecedented 8.4-meter primary mirror integrated with a 3.2-gigapixel wide-field digital camera system. The Legacy Survey of Space and Time protocol systematically images the southern celestial hemisphere every few nights across a decade-long mission timeline. Advanced machine learning algorithms process massive data streams in real time, enabling identification of transient events, near-Earth asteroids, and faint interstellar visitors within hours of observation. Rubin's enhanced photometric sensitivity extends detection thresholds to previously inaccessible magnitude ranges, promising discovery rates of dozens of new interstellar objects annually rather than current rates of one every few years. Automated processing pipelines utilize neural networks trained on millions of astronomical images to distinguish genuine cosmic phenomena from instrumental artifacts and atmospheric interference. This technological revolution enables detection of interstellar visitors during approach phases months or years before closest approach, providing unprecedented preparation time for detailed observation campaigns. Theoretical implications. 3I Atlas detection catalyzes profound theoretical implications across astrophysics, astrobiology, and SETI research paradigms. Statistical analysis suggests these discoveries may indicate a broader population of interstellar travelers, potentially including artificial constructs deployed by advanced civilizations. Galactic archaeology models now incorporate possibilities of technological artifacts traversing between stellar systems, fundamentally altering understanding of interstellar material exchange mechanisms. The concept of automated probe networks gains credibility when considering the efficiency advantages of robotic exploration versus biological travel across cosmic distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, systematically monitoring emerging technological species while maintaining operational security. The temporal correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about directed observation versus random encounters. These paradigms suggest humanity may be embedded within a complex, interconnected cosmic ecosystem where intelligence actively monitors and potentially influences emerging civilizations through strategic deployment of monitoring technologies. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's inaugural attempt at planned rendezvous with interstellar visitors, utilizing advanced trajectory prediction algorithms and rapid deployment capabilities. International coordination protocols integrate ground-based observatories with space-based assets, creating real-time global response networks optimized for comprehensive data collection during rare encounter opportunities. NASA's proposed rapid response spacecraft concepts could achieve launch readiness within months of detection, employing ion propulsion and gravitational assist maneuvers to intercept objects before solar system egress. Project Lyra, designed for Oumuamua pursuit, demonstrates technical feasibility of interstellar chase missions using current propulsion technology and precise orbital mechanics calculations. Advanced sample return architectures would enable direct laboratory analysis of interstellar materials, potentially revealing formation conditions in alien stellar environments or evidence of artificial construction techniques. Future missions deploy sophisticated analytical instruments including mass spectrometers, neutron activation systems, and high-resolution imaging arrays capable of determining composition, internal structure, and manufacturing signatures with unprecedented precision. These endeavors position humanity for transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about cosmic intelligence. The technical analysis of interstellar visitors like 3I Atlas continues pushing the boundaries of aerospace engineering and astrophysics. As detection capabilities advance and propulsion technologies evolve, we approach revolutionary discoveries about advanced materials, exotic physics, and potential cosmic intelligence. Whether these objects represent breakthrough technologies or exotic natural phenomena, they're already transforming our approach to interstellar exploration. Stay connected with Stellar Tech as we decode the engineering marvels hidden in cosmic mysteries and explore humanity's technological future among the stars.